Good morning. Thank you. Good morning, sir. Okay, okay, I'll call you. Yes. Okay, sir. With key. Yes. Good morning, class. Sorry for that delay. Today, actually, we'll be interacting more. Trying to put to action some of those expressions that we have already, getting you acquainted with them so that you are good to go by way of being able to use them effectively to solve questions. So let's try to complete our slide. I want to believe many of us are online right now. I want to believe many of us are online right now. We'll be taking the attendance. I'm very sorry for coming late. So we have to move to another venue, actually, trying to get this lecture on. And today will be very, very important, at least for as many of you that are able to actually attend the lecture. Because really we'll be taking time to solve some problems, problems that I know will be very useful for you. Problems that will be very relevant, that if you remember it will help you. So we are going to slide. Last time when we were having a lecture, there was a power outage. I pray there won't be power outage today so that I can have a smooth lecture. Towards the end of the lecture, we had a power outage. So this morning, we'll talk about the flow rate being constant, arising from the equation of continuity. And then, of course, we also have the mass flow rate also being constant. So these are the two equations that we have on the board. Equation of continuity arising from, or trying to tell us the volume flow rate, and then the other one talking about mass flow rate. And of course, the SI unit of mass flow rate is the kilogram per second. Kilogram per second. So let's take attendance. The first code for attendance. The first code for attendance. I want to believe you can hear me loud and clear. I want to believe you can hear me. This is 103. Like I said earlier, it will be interactive. And of course, it will help you, like I said, to actually understand the question, especially the one that will be my own section. So the first code, attendance, C-A-K. double Z, all capital letters, C A K double Z, C A K double Z, C A K double Z, that is Z Z, C A K Z Z. Okay, so let's move on. So we have the mass flow rates, and that takes us to what we call the Bernoulli's equation. It's applicable to what we have on the right. You know, I have a figure on the right hand side, and that figure actually can be the flow, trying to show the flow of fluid, through different sections and elevated, at say a particular height, y. That is, one is on the level, the other one is on another level. So you can see there that we have the blue part, the deeper blue. That's why we have the input. You can see the level, that's y1 in figure A. Let's try to look at, after moving the distance L, that's capital L, that is now moved to a higher level, say y2. That is at an instant t, and then at a later time of flow of that fluid at theta, at t plus delta t. So if you look at the volume V, colored an analytical volume color green in the figure, emerges at the right end. The emerging volume must be the same as the entering volume because the fluid is incompressible, same constant density rho. So if the fluid flow at a steady rate through a length L of a tube from the input end at the left to the output end at the right, from time t in A, that's in that figure A, in that figure A, you see that at a level y1, we have v1 and then say p1. So when it is now raised, that is when the fluid flows to a raised level, say raised to y2 with velocity 2 and p2. The amount of fluid shown at the input will just be equal to amount shown at the output end. So in A, we have the input end, and then in B, we are looking at the output end. So if you look at that, there's an equation due to Bernoulli, and that equation says the pressure at level 1 and the energy density, kinetic energy density at that level plus the potential energy at that level. So Bernoulli equation, you must take note of that, actually tries to relate pressure with kinetic energy density and potential energy density. I'm saying energy density because instead of using mass, as we all know, for the objects, if you are talking of a solid, when I want to write the kinetic energy for an object, I just say half mv squared. But if I'm talking of a fluid, it's not just that mass, it's mass per volume. And mass per volume is what? Rho. So instead of M, I'm now using rho. If you remember, at the beginning of this lecture, to characterize fluid flow, what do we use? We use density and pressure. Unlike when I'm talking of solids, where I will use, instead of density, I'll say mass. Then instead of pressure, I'll say force. So for solid, I can characterize the solid using mass and force. And I will write the Newton expression, quite easily. Quite easily. That's if I'm talking of solid. But because I'm talking of fluids, instead of mass, I'll talk of mass per volume. And instead of pressure, I will talk of, instead of force for solid, I will talk about pressure for fluid. So you will see that I'm now trying to write an expression relating pressure and kinetic energy density and potential energy density. I'm not saying potential energy now. I'm saying potential energy density. Because instead of mass, I'm now using mass per volume. And what this expression is saying is that the sum of pressure at a level 1, the sum of its pressure, kinetic energy density, and potential energy density is a constant. That is, I can look at it at different segments, at different heights, along the flow. So this expression is what we call kinetic energy density. So if you hear population density, means population over an area. But because I'm talking of fluid, not as something that is discrete, fluids are continuous. Okay? So I'm now saying I'm talking about kinetic energy density. So I hope Bernoulli equation is now very easy. I can remember it readily because it relates pressure with kinetic energy density and potential energy density. Pressure, kinetic energy density, and potential energy density. And actually, their summation, the summation of the pressure, the kinetic energy density, and the potential energy density is a constant. That's what I have in that figure. So you see that if there is no level change, okay, if the something is horizontal, what happens? Y will be 0. And so the potential energy density will be 0. Can you get that in that expression? Do you agree with me from what we have in that expression? I hope you agree with me with what we have in that expression. That is, if the container or the tube through which the fluid is moving, if it is on the horizontal, that is, the fluid is just flowing. So that means the potential energy density will be 0. And of course, again, if you apply Bernoulli equation to fluid at rest by putting, say, velocity is 0, what happens? If you substitute that, let's go back to this expression. If the speed were to be 0, I don't know whether I can get this equation I want you to look at. In this equation, the only equation you can see now, if speed were to be 0, if it were to be 0, that is, the speed of the flow were to be at rest, that this expression will reduce to our previous expression. Do you agree? Do you agree with that? Because I will transfer the potential energy density to this side, to the right-hand side, and the pressure to the other side. And the kinetic energy density in that wise will be zero. So what is left is the potential energy density on right-hand side and pressure of or difference in pressure on the left-hand side. And that will be like what we call the gauge difference or the gauge pressure. In which case, let me try to write that expression. I don't know if you can see the paper I'm holding. Can you see the paper I'm holding? I want to write something on that paper. I want to write something on that paper so that you can see. There's an expression I want you to be conversant with, and I'm going to write it on that paper. I don't know whether you can see this. Change. Can you see? Can you see what I wrote there? That is change in P. Change in P is equal to rho GH. Rho GH. Change in P is rho GH. What I want to just say is this expression is similar to the expression we see before. This expression, let me show you the expression that is similar to it that we have before. We have an expression before that is very similar to that Bernoulli expression. If the fluid is at rest, it's just similar to what we have here. I don't know whether you can see what I'm trying to put the arrow for you to see. Or this is still the same. That is, in that Bernoulli, we are saying P1, this is P2, and V is 0. So by the time you take rho GH or rho GY1, you take it to the other side. It will be rho G Y2 minus Y1. That is, you factor out the rho and G. So Y2 minus Y1. So Y2 minus Y1 is just H. So this expression that we have here is a consequence of or is inherently embedded within the Bernoulli equation. So the Bernoulli equation is just a general form of equation that before now we know very well. And the equation I'm showing you are the equation you need to solve problems. Many of the problems that will come across under my own topic, you need that expression. You need that expression to solve many of the problems that will be given to you. So this expression due to Bernoulli, if I take, I don't know where I can see my arrow here. Can you see the arrow? The arrow. That is the mouse. So if this is 0 and this is 0, that is for fluid at rest. That is, this is 0. This is 0. So if I take this rho G Y1 to this side, to the right-hand side of the equation. So I'll factor out rho G. I will now have Y2 minus Y1. And Y2 minus Y1 is just H. So I will now have something like P1 equals P2 rho GH, like what we have before. So that expression I must know how to write it very easily. And Bernoulli expression also, I must know how to write it also. So Bernoulli equation to fluid at rest is just like what we have before. Like what we have before. Okay? So a major prediction of Bernoulli's equation emerges. If we take y to be a constant, say why not? That's why not. So that the fluid does not change elevation as it flows. So, what is that telling us? That is, if we say, okay, why we now have the pressure, kinetic energy density being a constant. That is, at one level, the pressure plus the kinetic energy density will be equal to the pressure and kinetic energy density at another point. So we should know that as well. So this expression now, explain that. If the speed of a fluid element increases as the element travels along the horizontal streamline, the pressure of the fluid must decrease, and the converse is also true. If the speed of a fluid element increases as the element travels along the horizontal streamline, the pressure of the fluid must decrease. In another way, where the streamlines are relatively close together, you understand what I mean by a streamline now? The paths of an element along the flow of the fluid. Okay? And of course, another part, the velocity is tangent to it. I hope you still remember. We dealt with that in our class, I think on Monday. So, where the streamlines are relatively close together, like when I show you, so the velocity is much, the pressure is relatively low. Do we agree with that? Where the pressure is great along the flow, we are saying the pressure is very low. That's from Bernoulli. Okay? So for an ideal fluid, we know an ideal fluid is incompressible, having a constant density, lacks viscosity, that is, there is no friction, so that's a smooth flow, and its flow is steady, that is, constant speed, and of course, is irrotational. And of course, again, we define a streamline is the path followed by an individual fluid particle, and then a tube of flow is a bond of streamlines. So let's take our attendance again before we go for some questions. Attendance code number 2. Attendance code number 2. What's written on the paper is just change in pressure. That is pressure. I can say, do you want to write it down? Write it down. The person writes, or the person was saying, you can't see what's in the paper. Just write change in pressure. You don't have to write change. That's delta P equals rho G H. Delta P equals rho G H. Okay? Can you take that down? That's what I wrote in the paper. Delta P is equal to rho G H. And instead of that delta P, you can now make it, say, P2 minus P1 equals rho G H. Can you write that also? Instead of delta P now, put P2 minus P1 equals rho G H. Can you write that? Okay, write that. So now take that P1 to the other side of the equation. If you take it, what will you have? You have P2 equals P1 plus rho GH. Please know how to write that expression, especially for my own questions. Okay? It's very good for you. Do you understand what I'm saying? So let's go. And of course, from what I asked you to write, you can see clearly that that is what I have in the paper, or what I now dictated is like what I'm pointing to here. Okay? It's like what is there. It's like what is there. I hope you agree. It's like what is there. This one. P2 equals P1 plus rho G. This is Y1 minus Y2. It depends. Maybe you can say Y2 minus Y1. Doesn't, the other depends on the way the question is. I hope you understand what I'm saying. So let's take attendance 2. Attendance 2. Code 2 now. 4 V 4 V B M 6. Let me take that again. 4 V B M 6. 5. That's 5 letters. No, there are figures there too. Or 5 characters. Let's put it that way. 4 V B M 6. 4 V B M 6. It should be capital letter. Capital letter. Yes, somebody wrote that correctly. That's David Godwill. Correct. 4 V B M 6. Make it capital letter. It should be capital letter. Okay? 4 V B M 6. So let's round up. I want to give you some questions. I will read it, I have it on the paper. Let me give you a question. You want to write down the question. I want to give you a question now. Like I told you, you must know how to write that expression correctly. You must know how to write that expression correctly. And any question given to you, just see how that expression can fit into that question. You'll be able to solve it. You'll be able to solve it. I mean, very easy. So let's take down the question. Calculate the hydrostatic difference in blood pressure. Calculate the hydrostatic. I hope you are taking it. Calculate the hydrostatic difference in blood pressure between the brain and the foot in a person of height 1.83 meters. Let me take the question again. Calculate the hydrostatic difference in blood pressure between the brain and the foot in a person of height 1.83 meters. Given that the density of blood is 1.04 times 10 raised to 3 kilogram per meter cube. Do you want to take that again? Calculate the hydrostatic difference in blood pressure between the brain and the foot in a person of height 1.83 meters. Given that the density of blood is 1.04 times 10 raised to 3 kilogram per meter cube, and acceleration due to gravity is 9.8 meter per second squared. That's question 1. Please know how to solve the questions. Okay? Know how to solve such a question. I mean, one of you can try it and tell me the answer. Then question 2. Find the pressure increase in the fluid. Find the pressure increase in the fluid in a syringe when a nurse applies a force of 42 Newton to the syringe circular piston, which has a radius of 0.9 centimeter. Find the pressure increase. I hope you are taking the question. Find the pressure increase in the fluid in the syringe when a nurse applies a force of 42 Newton to the syringe circular piston, which has a radius of 0.9 centimeter. That's the question. Then the last question now. I want to believe one of you will be able to solve the problem quickly. Let me give you the last question for today. On Friday, I will still give you more questions. If I were you, I will take time to solve those questions. Okay? I will take time to solve those questions. So the third question is now, what gauge pressure must a machine what gauge pressure must a machine produce in order to suck mud? You know it's sucking. Spelling of suck now. S-U-C-K. Because it's sucking, you know that pressure will be negative. You know we said gauge pressure can be positive or negative. But if the pressure is just moving the fluid, you know, it will be positive. But if it's sucking it, it will be negative. Take note. So what gauge pressure must the machine produce in order to suck mud of density 1650 kilogram per meter cube up a tube by a height of 1.5 meters? Sorry, what gauge pressure must the machine produce in order to suck mud of density 1650 kilogram per meter cube up a tube by a height of 1.8 meters? Yes, some people are already solving the problem. That's very good. Very good of you, Abolaji and Adeyemi. Very good. At least you are making efforts. I want to believe others too are making efforts. As you are making effort, you are already making effort to say, I want to pass this exam. I want to pass. That's what you are saying. And for those who are evading it, you know, too bad, too bad, too bad. So if I were you, I would take time. I will solve those problems. You know, I told you the problems are at the back of Valley Game. You go there, you get those questions. There are many. You know, like I told you, the problems can be up to like 90. But I've taken my pains to actually look at some questions there. And like I told you, in certain questions for you, if as an examiner, you know I'm an examiner now, I'm the one to give you questions. So if I want to set 10 questions for you, I will set like 4 that will be based on statements like the following. You know, this is a statement, all these are statements, all what we have on the screen. Now, they are statements, and those statements you must know them. If you don't know them, some of the questions you'll be able to solve. So, if I'm to set 10 questions, I will set questions that borders on statements, about 4 questions, or 5, 4 or 5. And then the remaining will be questions we have to solve. And many of the questions for us to solve in this our class, many, I'm not saying all, borders on this expression. I mean, we know that expression long ago. In fact, many of us that are very good during our own level, we know them. This pressure at a given depth is rho GH. But that rho GH is when I'm talking of pressure at that point. But actually, most times what we look out for is change in pressure. That change in pressure is rho GH. Okay? So instead of that change, and I'll say P2 minus P1 is equal to rho GH. Rho GH. And so therefore, I can now rewrite it and say P2 is equal to P1 plus rho GH. And I'm okay. And then today, we've introduced one other thing. We call it Bernoulli equation. In our last class, we talked about continuity equation. But today, we are talking of Bernoulli's equation. Continuity equation in our last class is talking about the preservation or the constant of the volume flow rate or mass flow rate. That is, at one level, at one point of flow, the speed and cross-sectional area should be equal to the speed and cross-sectional area at another point. Indirectly, we are saying U, that's U for speed, and A for the cross-sectional area, is a constant. And on that day, I also stress that the speed and the cross-sectional area are inversely related. I hope you remember. The speed, the speed, the speed, the speed, and the cross-sectional area is a constant. So let's have the third code in closing. Let's have the third code. One of you is a doubting Thomas. You say, your fellow colleague said before test and nothing came out. No problem. You can be a doubting Thomas. It's good. So the third code, M2 W X Z. M2 W X Z. M2 W X Z. That's the third code. M2 W X Z. So I've given you 3 questions to solve. I've given you 3 questions to solve. Please take time, solve them. And in our next class, I will still give you more questions to solve. So by the time you have more and more questions, I believe, you know, it's a pool, unlike in those days. In those days, Each examiner will just set maybe 5 questions for you or so. You know, we are 6. By the time each person sets 5 questions, that will be like 30 questions. And then it will be in paper. You have it. But now the questions are more because you want to use computer. Because computer will randomize. It depends on what you pick per time. But I can tell you, in my own section, if you are able to pick it, if your computer can pick, it will pick something you know, if possible. Density is a constant. And of course, we can actually deduce our gauge pressure from the Bernoulli's equation. If we assume that the fluid is at rest, so that term for the kinetic energy density will disappear. So the only surviving time will just be pressure and potential energy density. And by the time you look at the 2 levels at different points, you see that what you have will just be the gauge pressure. That means change in P being equals to rho G H. Okay? Please, any question? We are rounding up. Please, any question? I'm trying to read from your chart to see which of them. Okay. One of you even help others to write the questions, especially the first and the second. I don't know whether you are able to get the third one. Okay, let me give you the third one. It's like you didn't get that. Let me. Abolaji and then Abidoyi, 2 of you were able to